Hey guys, hello everyone and welcome to the channel. So today in this particular video we are going to discuss 10 tricky questions which were asked on inorganic spectroscopy, right? Now inorganic spectroscopy is one of the very high weightage topic from your inorganic chemistry. Apart from your coordination chemistry and organometallic, the third highest weightage topic is your inorganic spectroscopy. Topics like EPR spectrum, Mössbauer spectroscopy, inorganic NMR, all these, and also your IR spectrum. So all these topics comes under your inorganic spectroscopy. So we will try to take some questions which were asked in the previous years of CSIR NET exam, and we'll try to see that how to solve them. So before wasting any time, let's start with it. Alright, so let's take this first question, and this question was asked for 4 marks in your CSIR December 2019 exam. The question says that for an octahedral copper plus 2 complex depicting axial EPR spectrum, okay, so that thing you have to focus on, that it's an axial EPR spectrum and it's an octahedral complex. That means your external magnetic field in this EPR spectroscopy is being applied along the axial direction of the octahedral molecule or octahedral complex. Now it's given that G parallel is greater than G perpendicular, and the geometry of copper plus 2 complex and the orbital containing the unpaired electrons are respectively. So both the things you have to tell. First of all, in order to answer this question, you need to know the basics of your G parallel, G perpendicular concept, and that I have discussed already in a particular video. I would recommend you to watch that, and I will attach that video on the right side of, on the right top of this particular video. I'll attach a link for that. You can click on that link and watch that video thoroughly for a quick revision of EPR spectroscopy and G parallel, G perpendicular concept, right? Now once you understood this G parallel and G perpendicular concept, what you have to do here, see, since it is given ki G parallel is actually greater than your G perpendicular, and if it is so, that means your electron density along the Z axis. Why? Because you know that in an octahedral complex, if I draw a octahedral complex of having these 4 ligands over here, so if I have ligands on the axial directions, so this particular ligands are along the Z axis, you know that, right? And your external magnetic field is also being applied along the same direction. So if G parallel is more, that means you have like the electron density, okay, electron density along Z axis is actually greater than electron density along xy axis, okay. So you have more electrons in the Z axis, and you know that in a particular complex, in a particular octahedral complex, if you have more electrons in the in the Z axis, so what will happen, that there will be repulsion caused between the ligand pair electrons and the electrons which will be there on the Z axis. So there will be a repulsion, and due to that repulsion there will be a stretching caused in the Z axis, like the axial bonds, and the axial bonds will become little longer than usual. This particular process is called as, and this particular process is going to basically form a tetragonally elongated complex, okay. So what you are going to get is tetragonal elongated or tetragonally elongated complex, okay, and the concept is called as Z out complex, right? It is a Z out kind of complex. So that means it's not tetragonal compressed, so you can cancel out option 2 and option 4. Now you have to tell about the unpaired electron. Where does your unpaired electron goes? So in order to answer that, you need to know the order of splitting of d orbital for your Z out complexes. So the order of splitting of orbital goes like this, that your dx square y square has the highest energy, and your dz square has a lower energy. It get stabilized because the bonds along the Z axis are longer, so that's why it gets stabilized. And then you have dxy, and the smallest ones are your dxz and dyz. So this is how you have your electrons filled in the orbitals. And now once you are okay with this, once you have made the electronic arrangement or the splitting of the d orbital, now you can fill the electrons here. So you have 9 electrons in copper plus 2 complex, so it's a d9 complex. So let's fill these 9 electrons. So 1 2 3 4 5 6 7 8 and 9. So that's how your 9 electrons will be filled. And if it is so, then we can easily say that your unpaired electron goes in dx square y square orbital, and that's how your option number 1 becomes your correct choice for this particular question. All right, so this is how we have to do this particular question. Let's go for the next question now. Alright guys, so let's talk about this particular question which was asked in CSIR December 2019 exam, and this was asked for 4 marks, okay. And the question says that the Mössbauer spectrum of the sample containing iron recorded in the presence of a static magnetic field, the number of possible allowed transition is. So in order to answer this particular question, I would recommend you to watch one of my video which I have made on Mössbauer spectroscopy. It's a 30 to 40 minute video. It's a short video, but I have explained everything which is based upon this Mössbauer spectroscopy, right? All the principle, all the concept and how it works. So each and everything is very much clear in that particular video. So it's highly recommended for you guys to watch that video if you have not watched that yet. If you will watch this, at least one of the question will be prepared for you, like if it will be asked from the Mössbauer spectroscopy. Alright, so the iron atom is given to us, and it's given key the sample is having this iron atom, like 57 iron is your iron, like this is your Mössbauer active, and it's Mössbauer active because it has two different I values for the ground state and for the excited state. Now we know that in the ground state its I value is plus minus half, and in the excited state it has a I value of plus minus 3 by 2. So that's the different I values which we have in the ground state and the excited state. Now in the presence of external magnetic field, what is going to happen, that there will be splitting of these energy level is going to take place. So this plus minus half is going to split up into two energy levels, and this will split up into your plus half and your minus half. So these are all different I values which I am writing, okay. And similarly this excited state is going to split up into 4 energy levels, okay. This is going to split up into 4 energy levels, and these energy levels will be like plus 3 by 2, then it will be like plus 1 by 2, then it will be minus 1 by 2 and minus 3 by 2. So that's how the splitting will take place. Now once you have understood and once you have done the splitting of these orbitals or splitting of these energy levels, not orbitals, energy levels, okay. So these states define the different nuclear energy levels in the ground state and in the excited state, okay. This goes for the excited state. Now if you have to see the transitions, so how many transitions are possible? So you should know the selection rule for making a transition. The selection rule goes like your delta I should be either 0 or plus minus 1. That's what is needed as the selection rule. So based upon the selection rule, if I have to do the transition, so from my plus 1 by 2, what transitions are possible? So from plus 1 by 2, so 2 plus 1 by 2, there will be one of the transition which is possible. Then from plus 1 by 2, there is one more transition which is possible to plus 3 by 2, because you can see the difference between the, like you have to subtract from the above to the below one, okay, like the higher to the lower. So plus 3 by 2 minus 1 by 2 is going to give you 1. So it's allowed transition. And same if you do this with this, so you are going to get one more transition which is from plus 1 by 2 to minus half. You can see this transition, you can just subtract it to check it out. So plus half minus half is going to give you plus 1, okay. So that's what it is. So delta I is following the selection rule is being followed in all the 3 transitions. So these 3 transitions started from plus half. Now you can check out for the other transitions which will start from minus half I value. So you can have a transition from minus half to minus half. So this will be one of the transition which will happen. The other one will be from minus half to plus half, and the third one will be from minus half to minus 3 by 2. So these will be the 3 transitions which will be possible from minus half. Now you might think that whether a transition from minus half to plus 3 by 2 is possible. You can check it out. Your delta I value will come out to be like 2, okay. It will come out 2. So that is going beyond your selection rule. So you cannot do that transition. So a transition from minus half to plus by 3 is not, plus 3 by 2 is not possible. So how many lines did we got? The total number of possible transitions which we got is 6. 3 from plus half and 3 from minus half. So overall 6 transitions is what we have got for this particular question. So this is how we have to approach questions from your Mössbauer spectroscopy. I hope you understood how it will be done. If you want a detailed explanation of Mössbauer spectroscopy, if you have not studied this topic yet, as I mentioned, do watch the video of the link is there in the I button. Click over there and also all the videos, like all the related videos, links will be there in the description of this video, so do check that out. All right, so let's go for the next question then. All right, so this particular question says that the expected number of carbonyl bands or your mu CO bands in the IR spectrum of facial isomer, and you have trans isomer. These are the two things which are given to you, and you have to tell that like how many different carbonyl frequencies you are going to get. Now these types of questions seems very simple, but they are little tricky. Okay, you have to take help of your group theory in this. I'll be giving you a table in which I'll explain you that, like, it will be just written that which particular isomer has what symmetry, like point group, and corresponding to that symmetry point group how many carbonyl bands you are going to get. Okay, because all the carbonyls does not seems to be equivalent in this case. So you have facial isomer and you have trans, this particular complex. Let's make both of them first of all. So for the facial isomer you will have molybdenum, and then you will be having a ligand backside, one front side, then this front side, and one back side. Since you are making a facial isomer, so let's make it as, let's make this as carbonyls. Okay, so these are the three carbonyls and these are your PPH3s. Okay, PPH3 are here. Okay, so that's what you have. So this is your facial isomer. The second one is your trans isomer, so that will be given like this. So let's make it a trans isomer, and fine. So if you draw this goes something like this. Okay, so you have to make these two PPH3 groups, so let's keep them on the axial positions. Okay, PPH3 groups, and then you have CO, 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 and CO. Okay, so fine, this is how the complex is actually. I can join them in order to show you the axial and the equatorial bonds. Okay, now the complexes are in this way that the point groups of this particular facial isomer is C3V, and the point group for this particular one is your D4H. Okay, D4H. Now once you are aware about the point groups, you can easily tell that how many like bands you are going to get. So based upon this table, you have to memorize this table in order to answer this. So yeah, based upon this table you can tell the answer easily. So basically you can apply a simple concept before going into that. Before like looking upon that table, I'll just give you a simple like concept. The concept says that if you have higher symmetry, okay, if you are higher symmetry in the particular molecule, so in that case it will have a lower number of IR stretching bands. Okay, lower number of IR bands. Okay, for the carbonyls. This rule is only for the metal carbonyls here. Now if you look for this particular one, which is D4H, in this particular case you can see that all these carbonyls which are there on the equatorial plane are actually having similar chemical environment and they all behave similarly. Okay, so how many peaks you will get in this case? So you will just get one peak in this case. Okay, because it has higher symmetry, that's why it has a lower number of IR bands. Now if you go for this particular one, it has like comparatively it has lower symmetry because C3V is a lower symmetry. It does not have perpendicular planes and all, so that's why this particular one is going to be have higher number of IR bands. And in this case you will find that these carbonyls which are on the equatorial planes are actually similar, or they behave as the same carbonyls because of having similar chemical environment, but this one being on the axial line will be different than the others which are on the equatorial lines. Okay, so equatorial ones will be different from the axial ones, so that's what it is. So how many peaks you are going to get in this case? So you are going to get 2 IR bands in this case and 1 for the trans isomer. Okay, so your correct answer should be 2 and 1, which is your option number 3. So 2 for the facial isomer and 1 for the trans isomer. I'll also give you that particular list right now. You can see on the screen, and in that particular list you can just figure it out. You can take a screenshot or you can just note it down that what kind of point group will be there or what kind of isomer is there and how many IR bands you get corresponding to that. Alright, so I guess this is much clear from that thing. Okay, let's go for the next question now. Alright, the next question is asked from your CSIR December 2018 exam, and it says that consider the species. These species are given to you: NO, I2, I2 minus, Cu2 plus and VO plus 2. It says that the number of paramagnetic species among them and the EPR inactive species. Okay, so they are asking that how many paramagnetic species are there and which of these species is EPR inactive. Alright, so two things you have to see. So first of all, let's find out that what is the requirement for a particular species to be EPR active. For EPR active species, you should have unpaired electrons in the molecule. Okay, so there should be unpaired electrons in the molecule. This is the basic requirement which should be there in the molecule in order to become EPR active. Okay, now once you have understood this paramagnetism, you know how to find it out. So let's try to do this. Now if I talk about these species, if I talk about NO, so how many total valence electron do I have in this case? So total number of electrons basically. So nitrogen is going to have 7 electrons, oxygen is going to have 8 electrons. If I just talk about valence electrons, so nitrogen has 5 valence electrons, whereas oxygen has 6 valence electrons. So total valence electrons in this case is 5 plus 6, so that gives me 11. So it's a odd number of like electrons. So obviously one of them is going to become unpaired, and that's why this is going to be paramagnetic. You can also draw the molecular orbital diagram for the molecules, for the diatomic molecules, and you can fill the electrons and see over there also, but this is the easy way to approach it. Okay, then if I talk about I2, so one of the iodine has 7 valence electrons. So if I just talk about total valence electrons, so 7 plus 7 is going to give me 14. So it's a even number, so that's why it's not going to be paramagnetic, it's going to be diamagnetic. If I talk about I2 minus, in that case your total valence electron will be 7 plus 7 and plus 1. 1 comes from the negative charge. So overall you have 15 electrons. Again, it's an odd number, so that's why it will be having some unpaired electrons. You know copper plus, copper 2 plus is there. So copper 2 plus has 9 unpaired electrons, right, or 9 valence electrons in the species. It's a D9 species, and D9, so it has 9 valence electrons. Again, it's a odd number, so it is going to become yeah, so this copper complex is going to become paramagnetic. If I talk about the next one, which is VO2 plus, so in that particular case, if I calculate the total oxidation state of vanadium, so that comes out to be vanadium in plus 4 state, and if it is in plus 4 state, in that particular case I can say that it's a D1 species, and if it is a D1 species, in that particular case I can say it has 1 unpaired electron. So those who have odd number of unpaired electrons, they are paramagnetic. So this is paramagnetic, this is paramagnetic, this is paramagnetic, and this also is paramagnetic. So those which I have taken down right now, these are all paramagnetic species, whereas I2 is a diamagnetic species, and you need unpaired electrons, or you need a species to be paramagnetic in order to become EPR active. So the species which is EPR inactive is actually I2. Okay, so iodine over here is that species which is EPR inactive, and the reason is that it has because all the electrons are paired up, it does not have any unpaired electron. So the number of species which are paramagnetic are 4: NO, I2 minus, Cu2 plus, and VO plus 2, and I2 is the species which is EPR inactive. So correct answer is option number B. Alright, so this is how you have to approach this particular question. Now let's take the next question from CSIR December 2018 exam itself. The question says that in the 31p 1H NMR spectrum, what does it mean? It means it's a 31p, that means phosphorus proton decoupled NMR spectrum. That means hydrogen is not going to couple with the phosphorus over here. Spectrum of the diamagnetic complex of this is a meridional complex which is given to you. M is some transitional metal, some transition metal where I value is 0. Expected number of resonances is, okay, so how many resonances you will be having in this particular case. Now first of all, let's draw this particular molecule. Let's try to make this molecule. So if I have M, okay, let me just make this like this. So I have M, and I'll be having ligands back side, and in the front side here also in the front side and then in the back side. So I can have the molecules in this way. Since I have to make meridional isomer, so I have to make like PR3 like this. I can put one of the PR3 over here, okay, PR3, and the third PR3 over here. That's how it will become meridional, and the rest of the spaces will be filled by the chloride ligand. So this is how my complex is. Now if I know about my complex, I have to find out that how many different types of phosphorus I have. The number of phosphorus is going to tell me the number of resonances. Okay, resonances means the different types of phosphoruses which you have in the molecule. So this particular phosphorus and this particular phosphorus will become like same. Why? Because if you divide it through this particular plane, if you consider this equatorial like molecule as a single plane, so you can divide this molecule into two equal half, reflecting both this PR3 on the either side of that, right? So if this is of type A, this is also of type A, but this PR3 is of type B. This is different than that because these are on the axial line, this is on the equatorial lines. So how many resonances are there? There are 2 resonances. So it was pretty simple, yet it was little confusing. The language was not easy to understand. The resonances over here tells that how many different types of species you have in that particular case. Alright, so this is how you have to approach this question. I hope this is much clear to you. Let's go for the next question then. Alright, so this particular question is again on your phosphorus NMR, and it says that 31p proton decoupled NMR spectrum of cis complex. This is the complex given to you. It's a platinum complex, and about platinum there is an information which is given to you that platinum has 195 isotope also, which is 33.8% in abundance, and it has I value of half, and its other isotopes are actually NMR inactive. So the other isotopes you don't have to consider, and your 31p, that is for the phosphorus, the I value is half. Okay, so that's what it is. It is comprised with the satellite peaks of A. So whose satellite peak do you have? Now when this question was asked in CSIR December 2018, there was a lot of like doubts, there were a lot of like different kind of opinion regarding this question, but I'll tell you in the best possible way that how you can approach to this. Okay, first of all, what you have to see that your platinum over here is given in 2 types. Okay, there are 2 types of platinum which is given to you. One is your platinum 195, okay, which is a less abundant isotope, which is 33.8% in abundance. Okay, this is the abundance which I have written, and it has I value, okay, it has I value of 1/2. Okay, so it is NMR active. Okay, that's what it is. The second isotope which we have is platinum 197. Okay, and this particular isotope is higher in like abundance. If this one is 33.8, obviously the other one will be around your 67.2, right? So yeah, that's what is going to be the other isotope. Okay, so fine. Sorry, it should be 66.2. Okay, so 66.2% of the abundance it will have, and since it is NMR inactive, so that's why I value will be 0 for this, because it is NMR inactive. Now if this particular platinum couples, okay, if this couples with your phosphorus, so what kind of, so who is going to split that? Now first of all you have to look in the complex, okay, that how does your complex looks like. So I'll just draw this over here. So you have platinum, with that platinum you have P Et whole thrice, then you have P Et whole thrice, then you have Cl, and you have Cl. Okay, that's how the complex is actually made. Now you can see that the phosphorus is going to get split because of the platinum over here. Okay, platinum is going to cause that splitting in this particular phosphorus. Now this phosphorus will split because of the platinum, and the platinum is of 2 types. So this particular platinum is going to split it into how many lines? So the number of splitting is calculated by this formula, that is 2Ni plus 1. Who is going to split? Platinum is going to split. And who is going to get splitted? So phosphorus is going to get splitted. Okay, so you have to make this thing very sure. So phosphorus is going to get, because you are doing phosphorus NMR obviously, right? So phosphorus is going to get splitted, and in how many lines? So that depends upon the I value of your platinum. So I value of platinum is 1/2 here, and since one platinum is only present and it's half and plus 1, so if you do that you get 2 lines. Okay, what do you get? 1 plus 1, so you get a doublet. Okay, you get a doublet. Whereas if you use this particular one, so this is when the platinum over here, which is the platinum in the center, is a platinum which is NMR active. Now it is also possible that the platinum which is at the center is NMR inactive, because in the molecule or in the sample there would be like number of these complexes, and all the complexes will have, because you know that if you just take 1 mole of complex also or 1 mole of substance also, you have Avogadro number amount of the complexes in that. Okay, so that means you just need to consider this thing, that there will be some options where you will be having platinum in the in the NMR active state, and somewhere it will be in the NMR inactive state where it will be as platinum 197. So here the number of lines will be like, if you just put it into an I plus 1, and if you put I value is equals to 0, it will just give you single line, so it will give you singlet. Now how does your peak or how does your spectrum is going to look like? That is going to depend upon the abundances. Okay, so what's the abundance? So here 66.2% is a bigger percent, so that's why this singlet which you will get will be quite bigger, and these doublet which are 33.8%, they are, since these are two peaks and their total abundance is 33.8, so that's why both these peaks are going to split into two smaller peaks of like 16.9. okay, so both are going to split into two peaks of 16.9%, and the central peak will be 66.2. so how your spectrum is going to look like? That is going to look something like this. Okay, it's going to look something like this. Now the abundance of the central peak, as I told you, 66.2%, these ones will be 16.9%, and this is also 16.9%. that's because these percentages are because this 33.8% is splitting into a doublet. Now let's come back to the question here. Okay, so this is how the overall spectrum is going to look like. Now the question says that it is comprised with the satellite peak of A. Now these smaller peaks, when the peaks are too smaller as compared to the main peak, this is called as, this bigger peak will be called as your main peak. Okay, so this will be called as your main peak. Alright, this will be your main peak, and these smaller peaks will be said to be satellite peak. Okay, these will be called as satellite peaks. Now since you have satellite peaks which are too smaller and the main peaks is quite bigger, so it says that satellite peaks of A, okay, of what? So these are satellite peaks of what? That's what is the question about. Okay, so they are comprised with the satellite peaks of what? So they are comprised with the satellite peak of the main peak, and what's that main peak about? So how does that main peak looks like, or what's the what is the nature of the main peak? So that is singlet. So the correct option for this particular question was singlet. Now look what people did in the exam, or what was the confusion in the question, that people thought that okay fine, this is up till where people tried to go with it. Okay, and yet they tried to make the molecule, or they tried to make the spectrum, and this is how the spectrum looked like, obviously. So they just thought that okay fine, we have got a triplet, answer would be triplet here. Or many people just thought that okay fine, it's talking about the satellite peak, so since we have got satellite peaks, so satellite peak is because of the doublet, so that's why the answer is doublet. But the question was asked in a twisted manner. The question was said that the satellite peak of what? Okay, it is comprised with the satellite peak of what? So of what is not written, but that's what the question is. So the satellite peak of the main peak, and the main peak is your singlet. So that's why option number B is your correct option for this. Right. So I hope this is much clear to you guys, right? Now let's go for the next question. Alright guys, let's talk about this question here. It is a little bit of misprint in this one. There are 4 different complexes which we have, and these are like you have MnCO6 plus, then you have CrCO6, then you have V, and then CO6 minus, and then you have like BH3CO. Okay, so that's what it is. So these are the 4 complexes given to you. They are asking the correct order of carbonyl bond length. Okay, that's what you have to answer. So first thing is, let's try to do the order of carbonyl frequency, because we are quite aware about this. We have studied that particular concept in a more rigorous way. So you know that electronegativity, okay, electronegativity, or you can just go with this, that electron density, okay, on metal increases. If the electron density on the metal increases, what will happen? That pi back bonding, okay, pi back bonding From where to where? Metal to carbonyl back bonding. Okay, this back bonding also increases. So as the electron density on the metal increases, your pi back bonding, that is from metal towards the carbonyl, this also increases. And since it increases, what happens? That the bond order of carbonyl decreases. And if the bond order of the carbonyl decreases, what happens to the bond length now? So you can go with the bond length now, right? So what happens to the bond length? If the bond order decreases, your bond length increases, because bond order and bond length, let me write down the orders, or let me write down the relationship. So bond order is proportional to bond strength. Okay, it's proportional to your carbonyl frequency as well. Okay, it's also like proportional to the frequency of the two things. If we are talking about carbonyl here, so it's carbonyl frequency, and it's inversely proportional to your bond length. Okay, so this is what it is. Now if you look upon these complexes, this one is the one which is having a formal negative charge. Now if it has a formal negative charge, that means it has more electron density, so more back bonding and less bond order. And if the bond order is less, so what happens to the bond length? Okay, so bond length of CO increases. So if the electron density on the metal increases, you have more bond length of the CO. That's what it is. So if I go with this, if I just have to arrange these three, so I'll have this order, that VCO6 minus will have highest, then comes your chromium CO6, okay, then comes this, and then comes your manganese CO6 plus, because it is least electron, like it does not have that much of electron density on that, right? Now once you are done with these, you have to talk about this. Now if I have to arrange this particular part, that is BH3CO. Now this BH3 is, you know, it's a Lewis acid, it is electron deficient, it does not have that much electrons to donate it to anything. Okay, it instead of that, it will try to accept electrons. So it can never do this pi back bonding. So pi back bonding will, there is no chance of pi back bonding in the case of BH3CO, because instead of doing pi back bonding, it will try to accept electrons, because this is not having its complete octet. BH3 is an electron deficient species, it does not have its complete octet, it behaves as a Lewis acid. So since there is no back bonding, there is no possibility of the back bonding, so that's why this will be like, since there is no back bonding, so the back bonding will be least in this case. So the back bonding is least, bond order will be highest in this case, and the bond length will be least in this case. Okay, you just have to reverse everything. Okay, understood? I'm just explaining it once again. BH3, so back bonding is least in this case, you can just make this arrow downwards, least, bond order is highest, okay, because you have to just change everything, least, so it becomes highest, and the bond length will become least. So if I am writing the bond length order, so this is how it goes. So this is the least one, H3B and CO. So your option number 2 is actually your correct option for this question. Alright, so this is how you have to approach this particular question from your carbonyl stretching, and this particular one is actually from your organometallic compounds, but yet you should be good at solving these types of question as well. Alright, let's take the next question then. Alright, so this is one of my favorite question which was asked in CSIR December 2019 exam, and it was asked for 4 marks. Okay, it's a 4 marker question. Now what is the question about? It says that assuming that your JPH, that means coupling constant for phosphorus and hydrogen, is more than JPB, that means coupling constant between phosphorus and boron. So your phosphorus hydrogen coupling is more as compared to phosphorus boron coupling. Expected phosphorus like 31p NMR spectrum of H3P 11BCl3 is what? Okay, that's what the molecule is. So let's make the molecule first of all. So it will be done like this. You have like BCl3, okay, so this will be on the same plane, it's a planar molecule. So let's make it like this, BCl3. okay, now is BCl3 a stable molecule? No, it is a Lewis acid, it will try to accept a pair of electrons. So who will give that pair of electron? Phosphorus, obviously, okay, because it has lone pair of electrons, it will try to donate it towards boron in order to complete its octet and in order to make the molecule more stable. And now there are 3 hydrogens attached to this particular phosphorus like this, okay, just like the ammonia molecule, you have 3 hydrogens in the pyramidal shape attached to this. Now the shape and the other things does not matter, you just need to know that which molecule is attached to what. Alright, now if I just have to talk about this, if I just have to talk about the NMR spectrum, okay, that's what I have to talk about, and I am doing 31p NMR. That means whose NMR I am calculating, or whose NMR I am trying to find out? Phosphorus NMR, okay, make this thing very sure. Now who is going to split phosphorus first, whether hydrogen or boron, because both of them are attached to the phosphorus with the similar bond length or with the similar distances, quite similar distances. Phosphorus and hydrogen is also attached to each other by single bond. Phosphorus and boron is also attached through a single bond, like the bond distance is quite equivalent. So who is going to split first will be decided based upon this factor. So since JPH, that means coupling constant between phosphorus and hydrogen, is more, that's why who will split first? So these hydrogens are going to cause splitting first. And in how many lines are they going to split this? So they are going to split it in this. So 2Ni plus 1, just write down this formula, use this. So 2 into, since we have 3 hydrogens, so 2 into 3 into I value of hydrogen is half, and plus 1, if you calculate this, you are going to get like 3 plus 1, that is 4 lines. So it is going to split it into 4 lines, okay, these are going to be the 4 lines. And what kind of these lines will be, since the I value is half, so the ratio of these lines is going to follow the Pascal rule, and that's why the ratio will be 1:3:3:1. That's what it will be, okay. So these are going to be the ratios of the peaks, and this is the first splitting which will happen. Now what about the next thing? So next your boron is going to split this phosphorus, and in how many lines is it going to split? So again 2Ni plus 1 is the formula. So you have just one boron, and the I value of boron is given as 3/2. So let's put it as 3/2 plus 1, and if you solve this, you are going to just get like 3 plus 1, that is 4. It is also going to give you a 4 lines. But is the ratio going to be equivalent to the previous one? No, because now your I value is not half. The Pascal rule is only followed for I value is equals to half. Now since the I value for boron is 3/2, it is going to follow the non-Pascal rule, and the non-Pascal rule says that if you have 4 peaks or the 4 lines, and if you have to split them, the ratio of those peaks is going to be 1:1:1:1. That is going to be the intensity ratio of these peaks. So how is going to, like, how my peak is going to actually look like? So you have to first of all see that this is your phosphorus peak singly coming like this. Now what has happened, that first of all your hydrogen has splitted that. In how many lines? It has splitted into 4 lines. 2 of them are smaller ones, and like the central ones are bigger ones. Why? Because they are in ratio 1:3:3:1. Okay, so I'm just writing adjacent to that. So 1:3:3:1. Right now, next thing what has happened, that your boron has again splitted these lines into 4 more lines. So this has splitted into 4 lines, but what about the height of the line? So that is going to be equivalent, because the ratio is 1:1:1:1. All right, so this is how this has got splitted into 4 lines. Okay, so how my peak will actually look like? So the peak is going to look like something like option number 3. Okay, the 2 central peaks are longer, the adjacent or the end 2 peaks are smaller, and the intensity ratio of the smaller peaks, the 4 peaks which are there, they are actually 1:1:1. Why not option number 4 is correct? Because although the bigger peaks are following the Pascal rule, but the smaller peaks, that means the splitting of by the borons, these green lines are also shown by these tiny like peaks, and these peaks are also following the Pascal rule, which is not according to the I value. So that's why 4th option is not correct. Okay, so I guess you are quite comfortable with understanding these 2 things. So this is how you have to do this question. This was very good question. I like this question a lot. Okay, so yeah, this is one of the very good question from inorganic spectroscopy which has been asked up till now in your CSIR NET exam. Alright, okay, so let's take the next question now. Alright, so let's take the last question for this particular video. It says, now first of all, this question was asked in CSIR December 2017, okay, and same goes for the previous one. This was also asked in 2017 CSIR December exam. So this is something which is wrong in this, so just make sure that this is correct. Okay, fine. So it says that the IR spectrum of COCO4H shows your band at these 4 like IR bands. Okay, these are the 4 IR peaks which you are getting. It says that the frequency for your cobalt deuterium bond in centimeter inverse is expected to, okay, in this particular complex. Now if you just look upon both of them, so you can easily see that the frequency for cobalt hydrogen is actually 1934 centimeter inverse, because rest of them falls in the region of your carbonyl frequency. Only this hydrogen, cobalt hydrogen, or basically 1934 is in the hydride region, okay, metal hydride region, the frequency of the metal hydride region. So that's where it comes. Now you have found one of the thing, that is the frequency of cobalt hydrogen bond. You have to calculate the frequency of cobalt deuterium bond. You know the relationship between the frequency and the reduced mass. So you know that the frequency is inversely proportional to the reduced mass. If I have to do this, if I have to make this calculation, so frequency of COH divided by frequency of COD is going to be equal to under root of reduced mass of COD, okay, COD, and divided by reduced mass of your COH. Now if you put, you can either do the calculation by putting the value of cobalt and that, or you can just neglect the denominators, and you can just see that because you have M1 M2 upon M1 plus M2, so in the denominator you will be having the mass of cobalt plus the mass of deuterium, whereas in the denominator you have mass of cobalt plus mass of hydride, okay, hydrogen basically. So you can neglect the denominator terms, so you will only have M1 into M2 and divided by also M1 into M2, where in the above and below both side M1 will be your masses of cobalt, M2 will be the mass of deuterium in the numerator and the mass of like hydrogen in the denominator, okay. So that's what it will be. So basically mass of deuterium is 2, mass of hydrogen is 1. So if you put everything, you will just get root 2, okay. You can just put and solve. I am telling you a easy way to approach, okay, or approximate way how to approach that. So basically the mass, if you take the ratio of both of them, you are just going to get root 2. So if I use that particular knowledge and that particular data to solve, so I'll get frequency of COH divided by frequency of COD is equals to root 2, or if I have to actually calculate my thing, that is frequency of COD, this will be frequency of COH divided by root 2. I can put my values. The value is 1934 divided by root 2 is 1.414, and if I divide it with this term, I'll get 1396. So that is going to be my answer for this question, okay. So although this was quite comparable to your physical spectroscopy, but yet I have taken this question just to make sure that you know about how to solve these ones, right. So these were all questions from my side for this particular video, guys. Thank you so much for watching this video. I hope that you have learned few new things in this particular video. You got to know quite a few things, quite a like lot of things from this video, and if you like this video, give it a like, share it with your friends, and if you are new to this channel, do subscribe to the channel. I'll see you guys in the next video. Till then, have a great day and bye bye.